Okay, what we've been talking about is the ridiculous distances involved in space. Okay, space is a very, very large, spacey place. Last week we made sort of a human model going down one of the halls that illustrated just some of the scale distances in between things in our own solar system. What we're going to be looking at today are a few more things involved with distances and how we're able to figure out some of the distances between us and even more remote objects, and also a little bit having to do with the brightness of stars. So I'm going to gloss over this. I'm going to really try my hardest not to read slides to you guys because that's the worst when people do that. First thing about stars is there's a whole lot of them. You can go outside on a really nice night and there's not a lot of light pollution and you can lie on your back. You're not going to see this many stars. Reasons you're not going to see this many stars is because a lot of these stars aren't giving off light that is visible to you. Okay? A lot of that light that is visible to you is being blocked out by a thick atmosphere that we have. It's limited by just our ability to detect light with the naked eye. But even with maybe a good telescope or a good pair of binoculars, there's still a lot of this stuff you flat would not be able to see. Okay? Because it's giving off light that's not just visible light. There are a lot of different kinds of stars. We tend to think of the sun as being a good representative of stars just because it's the one we're most familiar with. But really, the sun, it's not the norm by which we judge all other stars. Okay? Take, for example, the star Betelgeuse. Okay, and we're going to take a look. Does anybody tell me what constellation we're looking at here?
Orion.
That is Orion. Very good. You can tell because he's got 3 stars in his belt. We're looking at the star Betelgeuse right here. Betelgeuse and Rigel are 2 of the brightest stars in the nighttime sky. Taking a closer look at Betelgeuse, say his name 3 times. There he is. Now this right here was taken using various digital imaging techniques that may have even been put together from kind of a composite of several different ones. You're not going to be able to see Betelgeuse in this kind of detail just with the naked eye or the telescope. But to give you an idea of the difference between Betelgeuse and our own sun, if this right here is the diameter of Betelgeuse, this right here is the diameter of from the sun to the earth. Okay? This is 1 astronomical unit. So this entire star completely swamps that distance. Not only that, if you take a look down here, this is the size of Jupiter's orbit from the sun. The star is even bigger than that. And it's nothing special. It's big, but there's some out there that are even bigger than that. Okay? And that's just, for instance, that's just one star out of, millions and billions of them. A few things you already know about stars. You already know, well, actually about distances. A light year is the distance that light can travel in 1 year. It's about 9.5 trillion to about 10 trillion kilometers. You also know about an astronomical unit. Okay, and that's the distance from the sun to the earth. We use that because it's close. It's kind of like using an inch because an inch is awfully close to how long your thumb is. Or, using a cubit. If you're back in biblical times, a cubit is how far it is from the tip of your middle finger to your elbow kind of thing. So astronomical unit is just a unit of measurement that we use because it's in. Another one we're going to be looking at today is something called a parsec. So by the end of today, you're not only going to know what a parsec is, but where the word comes from and how we came about figuring out what a parsec was. It actually is about 3 1/4 light years. Tell me what we're looking at here. We're looking at colors and lights, but can you be a little more specific? Especially if you've been in chemistry sometime in the last couple of years.
I know what you're talking about. I just forgot.
Spectroscopy.
Okay, spectroscopy. Exactly. You look through those little spectroscopes at lights, and it split the light up into different little spectral lines. What you're looking at right here are some sample spectral lines. When we talk about stars, so much of our, well, all of our knowledge basically has to be taken remotely because nobody has been to any star to gather a sample of its material, scoop it up and test it. We only know what we know about stars based on the light and the other emissions that they give off. And since light is caused by electrons and atoms jumping and falling and streaming and radiating light, like we've learned before, we can look at the spectrum of light coming from distant stars and figure out chemically what's going on in there. Now we're going to talk about something called apparent magnitude. Apparent magnitude has to do with how much light we can perceive coming from an object in space from here on Earth. Okay? This is a really weird scale because the bigger the number gets, the less visible a star or whatever it is you're looking at becomes. So for instance, something that is magnitude 2 is going to be easier to see than something that's magnitude 5. There are also some negative magnitudes, and the greater the negative magnitude becomes, the brighter something is. This actually goes way, way back to, I forget if it was Copernicus or if it was Galileo, maybe even been one of the ancient Greeks before then, who came up with a way of classifying stars by how much light, how bright they happen to be. I do know, based on what we're seeing right here, that if the magnitude of a star gets up above 6, you're not going to be able to see it without using some kind of viewing instrument. And so you can have some stars that are very, very bright in reality, but they appear very, very dim to us because they are so very distant from us. Okay, so again, apparent magnitude is how bright a star appears to be to someone who is observing it here from Earth, and then I got a really good picture here in a minute to kind of illustrate the difference between that and the actual magnitude of light. Another term we're going to look at today and just kind of touch on is something called luminosity. Luminosity doesn't have to do with brightness. Luminosity has to do with how much actual power is being given off by a star into space. And being a form of power, we measure luminosity in watts, just like we measure any other kind of power, because it is energy per time. In this case, it's energy per second. And so we say a star is highly luminous, that means it is giving off lots and lots of energy. So luminosity is more of an absolute quantity than just apparent magnitude. Apparent magnitude depends on where we are observing it, whereas luminosity is universal. You can rate something on a luminosity scale no matter where you happen to be or no matter where it is. And so because of that, luminosity is really a much better indicator of what's happening inside of a star, what stage in a star's life cycle it happens to be in, rather than how bright it appears to us. So the question is still out there, well, how can we figure out the luminosity of a star? How can we, being so far away from it, actually have any idea how much power, how much energy one of these stars is putting off? We're getting it. Now, there's some math here I really don't know too much about. I can kind of begin to grasp a little bit of it, but I'm not going to expect you to memorize formulas. I do know that luminosity of a star depends on two things. It depends on its temperature, and it depends on its size. I do know that the size is, and R right here has to do with the star's radius. Okay? And I know that there's a formula right there that gives us luminosity. It's equal to 4 pi r squared And I got no idea what that little dude is right there. It looks like a snail or a cannon. Snail cannon. T to the fourth. Okay? And T being temperature. I'm assuming in kelvins. What is the pi about? Anytime you see pi showing up in a formula, what is it for?
Circle.
Circles or spheres, right? And stars are spherical.
Circumference.
Okay, circumference, exactly. So, backing up there, this slide says luminosity is equal to the amount of energy every square meter produces multiplied by its surface area. So if I have a highly luminous star, then it already has a high temperature, which means it's going to be giving off heat. But if it is a large star, and every square foot or every square meter or whatever of that is giving off the same amount of heat, then it's going to increase proportionally the power it gives off the bigger the star gets. Now don't make the mistake of saying that if the object is really, really big, that it has a lot of mass. Okay? How big something is not mass. What is that?
Volume.
Volume, exactly. Okay, it's the other quantity of matter. You can have something that has very, very large dimensions, very, very big volume, and have very, very small mass. Okay, it talks here about having a gigantic marshmallow or a tiny football made out of lead, and they can both have the same amount of mass, but different volumes. Okay, and so when we talk about some of these stars being very large, they do have a large surface area. They may not necessarily have a very large mass. And their mass has to do a lot more with the life cycle they're going to end up following. We're not going to get into that today, but we are going to be talking about that soon when we do talk about the life cycle of stars. Ah, this is a flashback to 8th grade, right?
Oh, wow.
Have you ever seen one of these before?
It's been a hot minute.
It's been, oh, very good, because it does have to do with temperature. Very nice, okay, in Kelvin. Anybody remember what this diagram is called? Two really difficult to remember names, right?
Temperature graph.
It's like a map.
Isn't it like a, I can't remember.
This is a Hertzsprung-Russell diagram.
What?
Yep, or an HR diagram. Now, what this diagram does right here is it graphs two things. It graphs the surface temperature of a star, and it also graphs a star's absolute magnitude, which is something we haven't talked about yet. So maybe I'll talk about that first, and then we'll talk about the graph. We talked about apparent magnitude. That's how bright a star appears to be from our viewing point here on Earth. Absolute magnitude has to do more with how bright it would be if it was 10 parsecs away from us, or roughly 32, 33 light years away. But taking a look at this diagram before we delve deeper into that, somebody find Betelgeuse for me. Remember, he was a big red one. Where's he at?
Second big one.
Second big one toward the top right. Okay, excellent. There's Betelgeuse right there. What that tells me about Betelgeuse is that Betelgeuse is not a very hot star. However, it has a fairly high absolute magnitude, which means that it's giving off a lot of light. Now, in this case, if it's not hot but it is giving off a lot of light, that's because it's so hot and big. Okay? It has very, very high volume, very, very high surface area. Betelgeuse is what we call a red supergiant. Okay? Are there any other stars you see on this that you're familiar with? Any by name?
Polaris.
Yeah, there's Polaris, the North Star. Notice that it's high on the brightness scale, but it's not as hot as Betelgeuse. Funny thing about this, if you look on this bottom axis, is that it's actually backwards. The hotter stars are toward the left, and it cools off as you go toward the right. It's like they swapped this around and went backwards with it.
I see the sun.
Okay? Yeah, there's the sun. You see, the sun is almost as hot as Polaris, but it doesn't give off anywhere near the amount of light as Polaris, and so it's ranked further down here because it has much less luminosity. It's a much smaller star. In fact, if you take a look at this band that runs through here, this is what's referred to as main sequence stars. Most stars that we observe fall within this band right here. Okay, they're either really tiny and red and not very hot, not very bright, or they are bigger and bluer, which means that they are very hot and very bright. And then all points in between. Down here toward the bottom right, we've got Proxima Centauri. That is the next closest star to us after the sun. But it's not very bright, okay? Proxima just means close. Centauri means that it's in the, I believe, Centaurus constellation. Okay, of course now. A few other stars we see here, there's Sirius, okay, the dog star in Canis Major. He's decently bright. There's Vega. Remember the other one we were talking about that was very, very bright in Orion? Okay, it's a white main sequence star. But let's look at the difference between absolute magnitude and apparent magnitude. This next graphic is fantastic. Here's Canis Major as it appears to us on Earth. Sirius is the brightest star in Canis Major. Okay, it's called the dog star. If you were to put all of those stars at the same distance from Earth, it's actually one of the dimmest stars in that entire constellation. Why are all of these other ones not as bright to us here on Earth? They are much further away. Exactly. Okay? So do you see the difference between apparent magnitude, what we see here, and absolute magnitude, the way it actually is? Okay? That still begs the question, well, how do they know all this? How did they figure this crap out? Well, that has to do with something called the inverse square law. And I don't want to spoil it for you right now because we are going to be doing a lab, which will kind of delve into some of this tomorrow. Yes, I am? Okay. So I'm going to kind of jump through this real quick. Jump through, okay. Now let's talk about measuring the distance to stars, because if we're talking about how far away a star is, having to do with its actual magnitude, we need to figure out, well, we take the amount of light that's coming in and then do some fancy math and fiddle around with the distance. But that still doesn't tell us how we get the distance. Main way of getting the distance is by using something called parallax. This was mentioned last week in one of the videos that we watched. Remember the difference? If you've got two viewpoints, like say your left eye and your right eye, and you close one and you look at an object, then you swap and look at the other one, that object appears to shift. The amount that that object shifts is referred to as its parallax. The farther away an object is, the less of a shift you're going to have. If the object is very close, it appears to shift quite a bit. I love this diagram here. Here's the sun. Here is the Earth's orbit around it. And so the distance between the sun and the Earth is roughly 1 astronomical unit, 1 AU. During the course of a year, we swing from one side of this orbit to the other, which means that we've got 2 points of view that are 2 astronomical units away from each other. For some objects in space, that's plenty for us to be able to figure out how far away it is. Because let's say that we've got a star, and we measure the angle where that star is, say at this time of year, just getting into the fall. 6 months later, we'll just be getting into the spring. We measure it again. We take the difference in those angles and divide by 2, and that gives us this angle P for parallax. Now, those of you who survived physics, what do you notice that this is making right here?
A triangle.
More importantly, what kind of triangle?
Oh, a triangle.
Which means we can use what to figure out the distance? We can use trig, right? If we know this distance here, which we do, and we know this angle here, which we would, then you can use one of the trig functions to figure out, okay, well, what's this missing leg? And that's how we're able to figure out a lot of objects and how far away from us they are. Up to a certain point, because remember, the further away something is, the less the parallax is apparent. And so once you get out beyond about 1,000 light years, parallax really doesn't work. Fortunately, there is a lot of stuff you can see within 1,000 light years from here. If you're interested in where the term parallax comes from, it's on that slide. I don't care. Okay, talked about this. 2 astronomical units, that's about 300 million kilometers. That's pretty good. Again, it allows us to see things up to about 1,000 light years away. Again, the farther away something is, the smaller its parallax is. Now this down here is pretty important though. Distance and parallax angle are inversely proportional, which means as one increases, the other decreases. We measure parallax angle in something called arc seconds. Now, think back to when you were first learning about geography stuff. Think back to like latitude and longitude, right? Latitude and longitude are measured out in what units? Degrees, exactly. Now, what if you've got something that's between degrees? You know, what's the next unit that you go down to from there? Did y'all ever learn that one? Okay, so check it out. There's 360 degrees in a circle, right? No matter what plane you're looking at that circle on. Within each degree, it's broken up into 60 units called minutes. Okay? And each of those can be broken up into 60 units called what? Seconds. And so within each degree, you've actually got 60 times 60, or 3,600 seconds per degree. That allows for quite a bit of precision when you're looking at something like latitude and longitude. When you're looking out in space, remember, if you imagine that around us we've got this great big, imaginary globe. What's it called?
Atmosphere?
No, I knew it this morning. Like you look out and you see like this big, the celestial sphere. Okay? It's not actually a sphere, but it looks like one to us. It looks like a big ball going around us. Anyway, if you treat that like a big ball going around us, you can use degrees, minutes, and seconds to figure where things are positioned in the sky. You can also look at two objects in the sky and figure, okay, well, it's this many degrees, or this many minutes, or this many seconds apart. Okay, and it makes a little arc. So if you've got a star that you're looking at, and in the fall it's right here, and in the spring it is 1 arc second away from where it was, and you say that it is 1 parsec away from us. Okay, I just made that jump. Some of y'all need to wake up and catch this. 1 parsec is about 3.25 light years. So if the star's parallax is 1 arc second, then its distance is 1 parsec. Can anybody look at this before I spoil it and tell me where the word parsec comes from?
Part of the cycle.
You're close. Okay, the parallax. It comes from parallax of 1 arc second. Well, it is what it is. And again, the math does not work out just really well, because this is something that has been in development and has been used for, hundreds, if not thousands of years. Okay? And nobody likes to change a system once it's good and established. This is why we're still not using a metric system.
Oh, freaking not using that.
And it's only been a few hundred years on that.
That makes me so mad.
Anyway, don't get angry about, English units. It's not it's totally the English's fault, but that's fine. So, if a star has a parallax of 0.1 arc seconds, what is its distance? What you do is you use distance equals 1 over parallax. So its distance is actually going to be 1 divided by 0.1, so it's going to be 10 parsecs, which works out to it being roughly 32 light years away. Okay? Now, it takes you 6 months to make a measurement like this. Because you've got to make a measurement now, and then you've got to wait 6 months for the Earth to get to the other side of its orbit to make your second measurement, so you can figure out what the parallax is. But once you do, again, for anything that is within 1,000 light years or so from here, this is one of the ways that they figure out the distance of the deep sky objects. Okay. Now, am I going to expect you to be able to map all that? No, probably not, but I do expect you to at least know where it comes from, where the concept comes from. Okay? So are there any questions so far? Sure, people will have questions for me later after they wake up and watch the video, and that's fine. And since we're not getting into the life cycle of stars, that actually brings us to the end of the lecture today. Okay? Thank you all for paying attention, and if you think of any questions, let me know.